Oh yes, now I can hear you.
Perfect.
Sorry, my bad. Yep.
No worries.
Okay, how are you?
Good. How are you?
I'm fine. There is a great sunshine in here in Amsterdam, so it is definitely a great day. Because whenever there is some bit of sunshine, here everyone gets crazy.
And
So
it's the birthday of the king as well, no? I think.
exactly. Yeah, it was.
Or it was 2 days ago or something like that. No?
Yeah, it was on the 27th. So yeah, pretty much maybe the spring is coming. Hopefully, a bit late, but whatever. You're in Manchester, right?
I'm in Manchester, yeah, but it's raining a lot. I don't know if you can tell, but I went into the library and I got wet.
Okay, that's a bit less unfortunate for you. Okay, so I gave a small introduction about you, and so I said that you are pursuing your master degree in theoretical physics, right, at the University of Manchester, and that today we will be tackling the topic of dark matter, which sounds like a fancy topic, but yes, I would say it is very fascinating and extremely, I would say, not as fancy as it sounds like, but actually I would say very actual. So I would say we can jump into it. And I would ask you, as a beginning, as a first question, what is this fancy name? What does dark matter mean, and why did this material arise in first place?
Good question. Well, first of all, just to clarify, I'm by no means an expert in dark matter, so I'll try to do my best, and I think
yes, absolutely.
give you quite a useful information. But of course, I'm no expert. And regarding the question of what is dark matter or why it arises, I think the second question is more interesting, because if you solve the first one, you'll probably get a Nobel Prize. If you know what dark matter is, maybe one or more than one Nobel Prizes are coming for you. Regarding the second one, regarding why we think it exists or why we actually need it even, there's quite a bit of evidence, or more than evidence, quite a bit of things that doesn't work. First of all, the first discovery that led to believing that there was something else apart from baryonic matter, it was done by Vera Rubin, I think it was her name, and she discovered that the galaxies shouldn't exist. What I mean by this, I mean that as you go outside of the galaxy, you rotate with a certain speed. And this speed is, generally speaking, given by Newton's law. You don't even need general relativity. I think it should follow 1/√² of the radius or function like that. But what we see in reality is that these stars in the outer edges of the galaxies don't follow that distribution. They follow quite a different one. And we're quite certain about it as well. That was the first evidence. And of course, we didn't know what was going on. Then we also discovered that the luminical matter, so matter that we can see, and the mass of some galaxies doesn't quite match up. So we are missing quite a bit of mass as well for other galaxies. And now I think we also have evidence for lensing, so gravitational lensing. So essentially, when gravity distorts spacetime, bends light, and so thanks to this gravitational lensing, we can see things that are in theory behind a star or behind another galaxy. But we've seen gravitational lensing by nothing, and of course that means there is something there that is causing that spacetime to deform, but we cannot say what it is. It could be a black hole, for example, but black holes have radiation that we can see, as we've done recently. So it has to be something else. Okay. And that something else is dark matter.
Okay, so basically what you're saying is we, let's say, understood in first place there had to be this type of matter because we looked at galaxies, we saw that they had, at least in the outer part of the galaxy, matter should move at a certain speed. We compute based on the mass we could see. We saw how much mass there was and we calculated the velocity and we saw that numbers were mismatched. And according to the velocity, there should have been some other mass, some other matter, which is what we intend as dark matter. Okay, but then if it is okay, but if it is dark, okay, I mean maybe it is a very naive, name or even a naive question. But if it is dark, how do you observe it? How did we observe it? But in general, how can we detect it?
Well, first of all, we're detecting it by gravity. We know gravity is this matter is affecting gravity, so we know it interacts gravitationally by the gravitational force. Detecting gravitational waves and gravitational interactions is way more trickier, but we know that at least gravitationally it interacts with normal matter, with baryonic matter. And then we have three other forces. We have a strong force, weak force, and electromagnetic. We know it doesn't interact with electromagnetic force because it's dark, it doesn't emit light, or at least we think it doesn't emit light. Maybe it does, but really tiny amounts, we don't know. And it could interact via strong force or the weak force. And of course, if it does interact through those forces, we can detect it. As in, you said, if it's dark, how do you detect it? Well, you can detect things without light. We can detect things with other forces. So.
Okay. And looking up a little bit about say the definition or what people generally intend as dark matter. I have encountered let's say the definition of actually the distinction between hot dark matter and cold dark matter. What I mean, okay, it is let's say pretty self-explanatory as a name, but what are at the end of the day the differences between these two types of matter?
These two types of matter is hot dark matter is dark matter that is moving at relativistic speeds. So it's really hot, it's moving really fast, what we say. And cold dark matter, it's dark matter that it's moving at normal speeds, at non-relativistic speeds. And actually, there's quite a bit of evidence that hot dark matter cannot exist, or it's not the case, essentially, that we live in a universe with cold dark matter.
Okay, well, what is the evidence that there cannot be cold, hot dark matter?
It's mainly cosmological, I think, or only cosmological. There's, well, some observations. There's a function called the matter-Pau spectrum. If your viewers are interested or you're interested, you can Google it up. It's a function called matter-Pau spectrum, and essentially it's kind of a formula that you put in the matter and the elements that form the initial of the beginning of the universe, and you let it evolve. And when it evolves, it makes some predictions. And then you can make some observations and see what predictions match which observations. And essentially, we see that the observations match cold dark matter, not hot dark matter. So they would have quite different shapes, I believe. So that's, for example, why we discarded neutrinos as being dark matter. In the beginning, it was thought that neutrinos was a really, really good candidate, but we know they would have been ultra-relativistic than hot dark matter. And we know there can be hot dark matter, there cannot be hot dark matter, so it's not neutrinos, unfortunately.
Okay, how do these? So basically, I have done the last. I have recorded the last episode about the lambda CDM model and some other cosmology stuff. And so basically, the lambda CDM model is lambda cold dark matter, and we tackled the I would say how cold dark matter influences the expansion of the universe and the formation of, let's say, large-scale structures. Can you refresh us a bit of how cold dark matter does so, influences the formation of large-scale structures? And if we have, let's say, evidences or we have theories or hypotheses of how hot dark matter would influence formation of larger scale structure or even the expansion of the universe?
I'm pretty sure with hot dark matter we could. Well, no, I'm not gonna say it because I'm not 100% sure. But in essence, well, cold dark matter or dark matter in general is really important for the formation of structures. It's first of all, it's what 85% of the total matter. So in the beginning of the universe, it was the universe was radiation dominated, we say. So radiation was the main the main liquid or the main element of the universe that was guiding its acceleration, its expansion. But when you enter the matter era, which means you enter an era of that is dominated by the matter. Of course, cold dark matter being 85% of the total matter makes a huge difference. In essence, I'm not an expert in cosmology, and I'm just stating this as what I've learned in some courses, because for example, my master project is more about detecting dark matter rather than cosmology. But I think in essence, it's cold dark matter settles in. It forms some filaments to the universe, and then baryonic dark matter follows its gravitational potential, and it sits in that potential essentially, forming the large-scale structures that we see today, forming galaxies, clusters, etc., etc.
Okay, yeah, I find it curious that when they ran I think it was the Millennium simulation, I think it was called the Millennium Experiment or something like that. That they I would say simulated the large scale structure of the universe, so the cosmic web, so the famous picture that we see with all the cosmic filaments and the cosmic web in a big picture. We see actually pretty much a lot of I would say empty spaces, a lot of void that we do not I would say that we can't put there in the image nothing. There we can put matter in those voids, and so there has to be I wonder some inner relation between these empty voids that we see and dark matter.
What do you mean? As in these zones that are empty, it's because of dark matter, or?
Yeah, basically, how do dark matter influences the creation of these voids? Meaning, okay, we know that I would say large scale structure of matter, so baryonic matter has certain properties, but we do see, as you said, we do see that if we run a simulation, the Millennium simulation in this case, we take a sort of a simulated picture of the cosmic web. We see that there are filaments which are sort of tiny, which are made up of baryonic matter we can see, but there are big, let's say, cluster of space that are filled with nothing, at least in our images, are filled with with black. Okay, so I wonder how much does dark matter influence, let's say, the creation of these voids of apparent empty space for us, but which we actually say it is dark matter.
I mean, these empty spaces, again, I'm not an expert, but these empty spaces are probably empty. So what happens is kind of the other way around. First, the dark matter settles in and creates these filaments. And then baryonic matter, the matter that we can see, starts clumping in those filaments, already filled by dark matter. And so the empty portions are empty. Not that you have dark matter in there. Okay.
And how does it relate? How does it relate to, let's say, the other fancy similar term to dark energy?
You mean the relation between dark matter and dark energy?
Yeah.
Okay. They're quite different. Actually, most of their similarities comes from the name dark, and that's about it. So dark energy, in the other hand, it's not matter. It's just a type of energy that permeates the vacuum and makes the universe expand. Makes the universe expand faster than we think, essentially. Okay. So basically, is it related to the lambda of our cosmological model? Dark energy. Yeah, that's a sign you usually use for dark energy, lambda. Okay. So it is the force driving the inexplicable expansion then of our universe. Yeah. The cosmological constant that you are in these equations to make them create an accelerating universe, essentially. Okay. And do we have, let's say, we say that there is dark matter. We don't know what the hell this dark matter is.
do we have at least any proposal? Do we have any hypothesis of what this can be?
There are a lot of proposals. So you have dark matter that interacts strongly via a strong force. You have dark matter that interacts via the weak force. For example, the WIMPs, they were really, really famous in their time. Now they're a bit less popular, but are so-called weakly interacting massive particles. That is just massive particles that interact through the weak force. But then,
as I said, weakly interacting massive particles.
Massive particles.
Exactly. Massive particle, okay.
Then you have dark matter that interact via the strong force. You have dark matter that is annihilated into neutrinos, and we're trying to see if we can detect these hypothetical neutrinos to see if this dark matter really exists, and if it does, it really annihilates into neutrinos. That makes sense. But you have all types of dark matter. The problem is we haven't detected any.
And do you believe there are any, let's say, any hypotheses or any type of dark matter which are more suited than others, or at least let's put it this way, more believable to be dark matter? Are there any?
Mm-hmm. First of all, I think it's important to differentiate between two types of hypotheses. So you have like a hypothesis that dark matter exists and it's what is causing what we see. But there are other types of hypotheses that try to explain the same observations. These are the so-called modified gravity theories. And essentially, instead of adding this mysterious substance, they modify the laws of gravity to try generating the behaviors we see. Me personally, I mean, I don't know if you're interested in my opinion. Me personally, I'm a huge fan of these theories in terms of the mathematics behind them. But usually they're not as satisfying as dark matter itself. So for example, most of them cannot explain all the observations we see. For example, gravitational lensing is quite challenging to explain. And furthermore, there's no evidence. So it's quite hard to make an experiment to try proving or falsifying these type of theories, because they are usually quite similar to Einstein's general relativity. And so when you come to dark matter, then you have many proposals. What was the question again?
So it was, which are, if there are any more suitable candidates than other, and what are, let's say, let's call it the properties of these candidates.
Mm-hmm. So most of dark matter searches right now, what they're doing is the other way around. Instead of looking for dark matter, well, I mean, they think dark matter is somewhere, and of course they look for it there. But what they do is, okay, we haven't detected anything here, and so they exclude that region. They call it bounding the parameter space. The parameter space being just two axes. You have the cross section of this hypothetical dark matter. Cross section being the probability of interacting with your experiment, with your baryonic matter, and then in the other axis you have the mass of this theoretical particle. And so you can do an experiment, run an experiment, and see that you haven't detected anything. And you say, okay, so this region of this space is excluded because dark matter cannot exist here. If it was here, we would have detected it by this experiment. And that's how research on dark matter is going so far. We have excluded tons of regions. There are a lot to exclude, so we're working on that.
Okay. And what about? I know that. Okay, maybe this is completely wrong, but I know that at least I've read some excitement about WIMPs. What are the properties of WIMPs? Are they a suitable candidate for dark matter?
So they are a suitable candidate. Right now they're less popular than they used to be, but they were the first, maybe not the first, but one of the most believable candidates because of the properties of the weak force, and saying, okay, we have these massive particles that interact weakly, that don't interact a lot. So it's almost that as if they don't interact, which is what we see, that they almost not interact with matter. If they do, maybe they don't interact. And so that's why people are looking to them. Now there's quite a bit of bounds on that type of dark matter. And so they've become less popular. There are other theories and quite interesting ones. And so the focus has shifted a little bit. But there's still other experiments that try to make bounds on this type of dark matter.
Okay. What are, for example, any other proposals that are, let's say, overtaking the scene? Let's put it this way.
I'm not quite sure. You have tons of theories. So I know strongly interacting dark matter was also one that was coming up, but I think there's quite a bit of bounds on it as well. I'm not sure about the general picture nowadays, but the problem is you have tons of theories, tons of experiments, and just running and trying to discover it, essentially.
Okay, but how does then? Yeah, let's say how does okay, we have different theories, but we are not let's say very sure on any of these. How do we trace the distribution then without having a solid foundation? How do we trace the distribution of dark matter across the universe? And let's say, yeah, what are some methods that are used to map it?
So I think you're asking more about cosmology now, in a sense. So you can see Friedman equations, or well, some equations that are derived from general relativity. You can see them as a machine that you put some ingredients and they tell you what universe you expect at the end. And so that's what we're doing. The simulation of the millennium that you mentioned is essentially what it does. It puts some ingredients and tries simulating the universe right now. And not only the universe, but also a lot of quantities that we can measure. So for example, the CNV power spectrum, I don't know if it's a variable you've heard about, but it's probably the most informationally packed result of physics nowadays, and especially of cosmology. It's just a function, but you have a lot of parameters that influence that function. And you try tweaking those parameters so the function fits what we observe in the CMB, the cosmic microwave background. The same goes with the matter power spectrum, and the same goes with all the simulations run in cosmology.
Okay, and you mentioned a lot about simulation, but then at least with regards to dark matter, what is the role of simulation in studying dark matter, and how can different simulation, for example, the Millennium project, the Millennium simulation, how can this simulation be used to, let's say, to test the different theoretical framework that we want to put forward?
So in dark matter searches, there's quite a bit of cosmology involved, but most of it's experimental. And there's two types of experimental searches. I'm going to deviate a bit from the question, if that's okay. So this, I think it's essentially what's going to prove us right. It's detecting the dark matter, not just simulating it. Because we have really, really good simulations that already predict the universe the way they are. But if you don't detect dark matter, well, it could be anything else, right? So in the search of dark matter, you have direct detection experiments, which are, you put a huge detector made of, I don't know, a type of gas or heavy water or any substance that interacts with the type of dark matter you expect. And you just look, you observe for a year, 2 years, 5 years, 10 years, and try detecting the dark matter there. Then you have the indirect detection experiments, which are experiments that doesn't detect the dark matter directly, but it detects its products. So there are some types of dark matter that we think it could annihilate into products. So the same way the
you say it may lead to
it annihilates into products. Into other particles that are not dark.
Yes. Okay.
So we try to detect these products instead of the dark matter itself. So for example, there's theories that try detecting neutrinos. And if we detect some neutrinos that come from inside the Earth, maybe that's not neutrinos that are spontaneously generated inside the Earth. It's dark matter annihilating and generating those neutrinos, if that makes sense. Then you have dark matter annihilation into other types of particles. And they work the same way you would detect the Higgs boson. The Higgs boson needs a particle that you don't see in the detector itself, but you see its decay products, and so you know it exists. And these type of searches work the same way. In terms of simulation, of course, you can rule out, for example, hot dark matter, what we were talking about, but it's way harder to say if a particle is suitable or not, just depending a bit of the cross-section and a bit of the mass of the particle. Simulations are not so good at it.
Okay. As well, sometimes I get baffled at the actual importance of running a computer simulation to test basically every aspect of physical theories. And so I remind myself that before or after I should learn how to code, and that's.
The simulations are really, really useful, but it's also good to. I mean, I'm a huge fan of simulations on coding, but it's also good to remember that you have to detect it experimentally. Without an experiment, a simulation doesn't mean anything. So.
Okay. Now I want to ask you. Let's say let's make a sort of speculation, and let's say that we detect any type of dark matter or whatever it is. How? And I want you to be sort of speculative, if you want to be. But how do you think our understanding of the universe can change? Because as of now, you said that we didn't detect any. These are just hypotheses. We have some sort of let's say simulation that are leading us toward a certain direction to believing what dark matter can be. But whenever we will experiment officially, that I'd say the detection of dark matter, how do you think our understanding of the universe, of our place, can change?
Well, first of all, you would understand the totality of matter. And by totality, I mean, instead of understanding 15% of matter that we understand now, we would understand 100% of the matter. So that's quite a big improvement, I would say. Of course, from detecting it to actually understanding it, there's a big gap. So you would probably have to run a lot of other experiments and make some theories, etc., etc. In terms of our normal life, I mean, I don't think it would change that much. I think we would still go to uni and work and run our normal lives. But you never know. That's the thing. In CERN, for example, they detected the Higgs boson. Life hasn't changed that much. But to detect the Higgs boson, well, you first needed the accelerator of particles, which created internet, right? You made all of these great detectors that created a lot of technology companies that are now investing in quantum computers, in satellites, in any type of technology that we use in our daily lives. And the dark matter itself, I don't think it's going to have an awesome property that's going to heal cancer and allow us to teleport. But it's just more the way to discovering it than the actual fact of discovering it that helps humanity. Of course, it's also cool to understand the universe we live in, and and it may be important in I don't know, interstellar travels, but odds are in our lives we won't feel a great change.
Okay, but yeah, as you said, I think that I would say delivers a neat picture of the fact that if we can observe dark matter, then we will have, let's say, observed 100% of the type of matter that there is in the universe, so baryonic and non-baryonic, so dark matter. So yeah, I believe it is even though that is a problem for many area of mathematics, which is just doing mathematics per se, for the sake of it. Okay, for literally no other application other than the beauty of it. And I think it is at least it has its charms with every field. So yeah, hopefully we will still be alive when this will be the case. And with regards to this, I ask you, what do you think? What do you think are some, say, sort of timeline, quote unquote, of if we okay, said straightly, do you believe we can detect dark matter within our lifetime?
Yes, it's a possibility, of course. And there are a lot of experiments running, and there are a lot of experiments coming. So yeah, there's a real possibility of detecting dark matter in our lifespan. Saying a timeline or saying when it's gonna happen, I don't know. Can't help you with that. It's totally speculative. So, I mean, you can look at the Dune. I don't know if you've heard about it. It's a new experiment in the US. It's gonna mainly study neutrinos, but maybe that leads to understanding of dark matter. It's starting in not a lot of years. It may detect dark matter, yes, but I mean, you know, it's
But
totally
maybe not.
it's totally speculative.
Okay, and let's say, at least with regards to dark matter, what do you think are some, let's say, open problems? And I would ask you first, conceptually, what are some open problems with regards to our theoretical framework? And then, as you are, I think, more invested, what are some technical problems? So with regards to the detection, with regards to whatever it goes beyond the simulation, detection, whatever.
So in terms of theoretical problem, I don't think there's a lot of theoretical problem. There's a lot of proposals, and the main problem is how do we select proposals if we don't detect it? It's like saying we have 3 types of Higgs boson. How do we know which is the correct one if we haven't detected the Higgs boson? It's the same. And of course, maybe we don't have a framework for a theoretical framework for dark matter, but because we haven't detected it, we don't know. So I think the first step is experimental. And it's strange for me to say that. I'm more into theoretical physics, and actually my MPhil project, my master's project, is about detecting dark matter, but also kind of simulating how we could detect it. But the main challenges are in experimental. Essentially, the most important one is that if dark matter has a really small mass, for example, or it interacts not of times, it's really hard to detect, because, well, if it has a low cross section, so it doesn't interact at all, you maybe have to run an experiment for 100 years to have one interaction of dark matter. Who knows? That's the first problem. The second problem is that the detectors are not as good as we would wish. They're really good, but they have some threshold energies. There are some energies that below that you cannot tell what's happening. The detector cannot detect, essentially. And they are trying to improve the detectors, and there are other techniques to try lowering this threshold energy. But it's a fact that it's there, and it's a fact that it's an important issue if dark matter is not that energetic. I think those are the 2 main stones. Yeah.
Okay. Would you like to, how to say, proceed on to further studies, at least, let's say, with regards to this subject?
What do you mean, in my future career?
Yeah, in your, say, academic career.
Yeah. Actually, next year I'm starting a PhD in a different area, so it's not dark.
Okay.
It's about the anomalous magnetic moment of the muon. I don't know if you've heard about it.
Okay.
It's an open problem in particle physics, essentially. Do you want me to talk about it, or we can?
Yes, just for curiosity.
So essentially, there's a variable for every particle that is called the magnetic moment. It tells us
there is
a property of each particle.
There is a property. Sorry, no, I didn't understand.
Okay, so we have a property. It's called the magnetic moment, and this property essentially tells us how easily this particle aligns with a magnetic field, and we can predict these properties. And for example, for the electron, we predicted it was 2. We measured it, and it was 2, so everything was fine. And then we went to we went to his older brother, and the predictions don't match the experiments quite well. There's actually a deviation of 4.2 sigmas right now. 5 sigmas is discovery. At 5 sigmas, you can claim discovery. So it's almost there. And the problem is that we don't know why this discrepancy between experiments and the measured quantity. Experiments and the predictions, sorry. Essentially, the prediction is also 2 for the muon, but you have to take into account some contributions from the vacuum. There are some virtual particles and some processes that kind of screen the magnetic moment, and so they make it a bit different of 2. That's why we call it the anomalous magnetic moment, because it's not 2. It's defined as the magnetic moment minus 2 over 2, so that it's normalized. And we can also predict that variable, and that's really, really tiny, but we can predict it. And we can also measure it. And that's what doesn't matter. So what it tells us is either 3 things, I would say. The experiments are wrong sometimes. There's an underestimation of some uncertainties, or there's a cable that is not plugged in. Probably it's not this one. The second one is our theories are wrong. So our predictions are not precise enough. Our understanding of the vacuum is not good enough. And the third explanation is there's something else that is contributing to it, and we don't know what it is. Maybe it's dark matter. But it's some process that it's not in the standard model. So it's something beyond the standard model. And those are the 3 things that could have happened. If the uncertainty keeps increasing and it reaches 5 sigma, that would be the first evidence that we have of a process that is beyond the standard model.
What do you mean a process is beyond the standard model?
Well, do you know the standard model?
Yeah.
Yeah. So a thing that is not explained by the standard model.
Okay. Okay. So a physical process.
Yeah.
Okay.
The same way dark matter is not predicted by the standard model.
Okay.
If you detect dark matter, you would detect the first process beyond the standard model. So we would have two birds from.
Well, that is very cool. Then all the best and super good luck with that. Maybe you will come back here telling us a little bit about this process beyond the standard model. It would be nice. But you mentioned before quantum computing, and I want to ask you. Let's say I don't know what is your knowledge on anything related to quantum computing, but I have had this discussion, this debate with a friend of mine, and about quantum computing, which when it will be, let's say, fully embraced, not properly, because at the end, even now, I guess we are doing it properly, but when it will be fully embraced and exploited to the fullest extent, we will see, let's say, major and radical changes in pretty much very tangible aspects of our life. But also he was, let's say, this friend of mine was also more interested into the part which relates to consciousness, because we pretty much all know that consciousness, at least as of now, is really not computable. And so he said, if you can make it to exploit to the fullest extent quantum computing, then you may be able to track down the thing that is consciousness. Because he started, as many people do, started from the assumption that everything in the universe is computable. Okay, and which then I'd say a logical question, a reasonable question would follow is then, well, how do you compute consciousness? And that's just one thing I wanted to ask you. What do you think about this? Very personal opinion.
Personal opinion is really hard question. Extending a bit on that, I think there are some theories that I think that consciousness arises from some quantum processes. I think Roger Penrose is a defender of that, and actually he proposed it, I think. I think there's some evidence that in some parts of the brain, some quantum processes could be happening, and that could explain consciousness, maybe. In terms of simulating consciousness, well, what is consciousness? What means something is alive or not? Something is intelligent? It's hard. Quantum computing simulating consciousness. I think we have quite a bit of work to do to reach that point.
So maybe you think with regards to this, you believe that within our lifetime we will not be able to see it, or okay, not see it, but something close, let's say.
I mean, maybe I don't know. With the new AIs, it almost looks like we have already created consciousness, no? So maybe it's not that far away. But I think there are some big challenges in that. First of all, making a quantum computer that it's good enough, and that it seems pretty far away. So you would need a lot of qubits to simulate that, and so far the best quantum computers don't have a lot of them. So
okay,
there are some challenges. There are some challenges to sort out.
Yeah, and the last thing I wanted to, these are all let's say random question and debate within me and other people. But now there is another question I want to make you that I also made to the last guest, and I swear this to me I think is very pivotal for our future discoveries and pretty much our understanding of the physical universe. And it's the fact that we know that we can let's say we have one type of light, which is electromagnetic waves in all its different wavelengths, and we have gravitational waves, and then we have a messenger, which are two messengers, and then we have a third and a fourth messenger for the stronger and weak nuclear force.
Yes.
Right. Okay. Yes. And now I want to ask you. So I think we proved that gravitational waves can travel at the fastest at the speed of light. Okay, so we have as a universal bound the speed of light, the speed of electromagnetic waves, and which to me, if I think about it, I have a window, I watch over the window, and I start thinking about what you said before, the cosmic microwave background radiation. Okay, that was first light, let's say first light we could see 380,000 years after the Big Bang. But then I wonder, what was really before the Big Bang as well, which is equivalent to asking what is inside a black hole, okay, which are basically the question trying to tackle the boundary problem, meaning we have a boundary point, which is the Big Bang, before which we cannot see, let's say, and therefore before cannot communicate with us, and we cannot communicate with the interior of a black hole. Okay, and now that I think about it, there is also the sort of problem that we know that the universe, at least the actual universe, the size of the universe is actually much bigger than what the observable universe is, because we know, okay, the observable universe is 93 billion light years in diameter, but we know the actual universe is actually bigger. And then, so what I say, conjecture without any basis, I say there must be something else. There must be another messenger through which we can see in all different ways. We can see, or at least in a different ways that we can see, we can detect, we can perceive, because to be honest, the speed of light looks like a pretty limiting boundary that we have, and that's pretty much I would say the truth, because if we already said and we already acknowledged that the actual universe is actually much bigger than the observable universe, then yeah, I think okay, really we are not seeing much further apart in time and size. So what do you think? Do you think we will forever? Because the last guest I asked said from a classical point of view, I would say yes, we are forever bounded by the speed of light. We will never see beyond. But to be honest, I don't really like this answer. Do you think that? Do you generally have the same feeling, or I don't know?
Well, first of all, I don't think the universe cares about what we feel. No?
That is also that is also wrong.
But I don't think it is that big of a bound. If you think about it, the speed of light is quite fast for us. Maybe not for the observable universe, maybe not for the nearest star, but in our daily lives, even if we go to Mars, the speed of light is unachievable. We cannot dream of building a rocket that goes 0.9 the speed of light. So maybe it is a bound, but it's a bound that it's quite far away for us to reach or to even notice. Also, maybe it is not a bound. I think there's some theoretical work on some machines that could travel faster than light, in theory, just by folding space-time behind and
wormholes or not?
Say again?
Aren't they wormholes?
No, not wormholes, but just a device that could fold space-time, and that way you could travel faster than light. Okay. To be fair, it sounds a bit of science fiction.
Yeah.
And I think the theoretical model wasn't how do you say it? It wasn't stable, so it would just break when you step inside that rocket. There are proposals for it, but of course, we're too far away. As I said, I don't think it's something that worries me now. I don't think I'm affected by a lot by saying that the speed of light is maximum speed I can go. It doesn't affect me that much. It would be cool to know everything, but then physicists would have no job now. So no, but I think we're gonna die without a lot of questions answered. No? We have to learn how to live with that.
Okay, that's life, I guess. Okay, so thanks a lot for this time. I will let you go. I think we can wrap it up here. Thank you very much for this very interesting conversation. It was really completely my pleasure. Wow, thank you very much for being with us.
Thank you. Really good project. I really like it. So keep on going.
I'm happy. So yeah, that was the end of the episode 7, and I think we can end it here. And I will thank everyone who has been listening to us, and I will see you in the next episode. Bye.
Yeah.